Well, thank you, William, and thank you all for being here and for the opportunity to be here to speak with you. I'm going to be talking about a microbiology application, but it's image-based. And so I think it has broad applicability across anyone who does anatomic pathology or any type of digital or image-based, what we call clinical pathology. I think you call it chemical pathology here. Regardless, we're going to be talking about digitization and applying AI to images. I'm Bobbi Pritt. I'm a professor of laboratory medicine and pathology at Mayo Clinic in Minnesota. And I'm going to be talking about AI in action. And I think all of you know you're here in the session challenges with implementation, workflow, and standardization. And I'm going to be chairing this session as well. So let's go ahead and start. I recently published a paper with a number of colleagues. This was a joint collaboration between the College of American Pathologists, API, and DPA. We did a whole session on generative AI, which is not what I'm going to be talking about today, but it's definitely a hot topic. But a couple points that we mentioned from here is, first of all, right now, I think we all agree there's no true artificial intelligence. We call it more augmented intelligence. And that's what I'm going to be talking about today, is how we can use these tools to augment what we're doing. And in my laboratory, we're actually using it as a tool to help our technologists and our pathologists. So I really see this as a win-win, where we could take away boring, repetitive tasks and allow our staff to really focus on the things where their expertise is really needed. Now, another thing that we mentioned in this paper that we wrote is this quote from Dr. Ehrenfeld, who said, "It is clear to me that AI will never replace physicians, but physicians who use AI will replace those who don't." And we think that's true right now, and hopefully will remain the same that way, that we need to keep the human in the loop, that it is a tool for us to do our jobs better and help patients. So with that, I'll state that I personally have no disclosures. I will, though, be discussing some specific commercially available platforms, including those that we use in my microbiology laboratory, but I make no money from any of those. And I will also note that Mayo Clinic has collaborations with multiple different companies to co-develop AI algorithms. So AI in clinical microbiology, we're a bit like cytology, cytopathology, in that we're looking a lot at cellular preparations, and you can break the different categories down into two. We have the image-based applications in clinical microbiology, things like organism detection or rare event detection. So that could be looking at these lovely Giardia in a stool preparation. We could then enumerate them, do a score-based classification like a Nugent scoring on a gram stain. We can detect growth on culture plates. I won't be talking about this today, but we are doing this in my laboratory as well. And then there's a whole host of non-image based applications that I won't be talking about, but those include things like antimicrobial resistance prediction using AI analysis of mass spectrometry data or genetic sequences, detecting mutations in genes associated with increased pathogenicity, virulence, and even analyzing strain relatedness for outbreak investigation. But I will be focusing on digitization and AI in clinical microbiology. And even still, I will only be skimming the surface because of the time limitations. If you really want to read about this area, there are a number of review articles here written in just the past few years, and these slides will be made available to you later if you really want to delve in. So why digitize? I think all of you have probably asked that question and maybe answered it for yourself. If you're thinking image-based analysis, well, microscopy does remain the gold standard for detecting and characterizing many microorganisms. but it's manual and subjective. It requires highly trained and skilled technologists or technicians, as you may call them. And it takes in my laboratory about 6 months to get someone fully trained and competent to read the whole host of different preparations that we use in my laboratory for detecting parasites, blood films, and all those parasites on stool preparations. And you probably know that we have a national and actually a global workforce shortage on technologists. So it takes a long time to train these individuals. We lost a lot during the COVID pandemic when they retired and they just left the field altogether. So we have to make the use of, we have to maximize the use of the people that we have and make sure that they enjoy their jobs. So the challenge is training and maintaining competency, absolutely a challenge. The potential to miss rare positives if we are in North America, for example, or in Europe, the UK, are not highly endemic for parasites, but you're trying to find that needle in the haystack, that malaria case that you do not want to miss. And if most of the specimens you're looking at are negative, it's easy to miss the one positive that you may see that year. And then if you are a laboratory like mine, we're a high volume reference laboratory at Mayo Clinic. We do 200 to 300 stool specimens each day. So that's a lot of sitting at a microscope all day long. It's sort of akin to a cytotechnologist screening out pap smears all day long. You're looking for the rare positives, that metaphorical needle in the haystack, but meanwhile, you're sitting there at a microscope all day long. So how can digitization and AI help? Well, potential advantages, we were interested in looking at this to screen out negatives. In my laboratory, stool specimens are about 90% negative, 90 to 95%. Wouldn't it be great to just get rid of those and focus on the positives, allow our highly trained personnel to focus on those more interesting specimens? We also thought that we could decrease turnaround times, increase sensitivity, and maybe even facilitate teleparasitology, although we're not doing that yet, but my technologists keep asking when they can start working from home. So I'm going to talk about the Mayo Clinic experience, but in keeping in the theme with this session, I'm going to be talking more about implementation, validation, the pre-analytical process, training, and then also how do you maintain the quality of your work, proficiency testing, and what were our lessons learned. So even though I'm talking about an esoteric area with clinical parasitology, and I'm going to be focusing on finding parasites in stool specimens, I hope that you'll be able to take away some common ideas that would be applicable in your own practice as well. This is basically implementing digital scanning and then artificial intelligence. And in this case, it's to find parasites, but it could be to find mitotic figures or metastases or whatever applies to your area. So we were initially inspired by this publication by my colleagues out of ARUP Laboratories, Matheson et al. They developed a system to detect intestinal protozoa in trichrome stained stool specimens. And they used a deep convolutional neural network that had then been locked down for clinical use. And here's just a variety of the images that came from their scanner that the AI tool then identified. So this is a screening tool. In this particular instance, it is finding things for you. It has very high sensitivity. It is optimized for high sensitivity. So it's going to find more things than are actually there. And then positives are confirmed by traditional microscopy. Little different than some of the other applications out there. So they trained it on thousands to tens of thousands of exemplars per class. And so that would include like this. See, can you see my mouse? There we go. This little Giardia cyst or trophozoite. So thousands of those it was trained on. And their positive and negative slide agreement was about 98 to 99%. So very good. And it was more sensitive at finding parasites. We know AI doesn't get tired. It's going to tirelessly look through all those slides and find those parasites. So I was inspired by this, and we brought this and a different system into my laboratory to evaluate. We ended up going with this system, and this system is, they worked with this company called TechSite, who is here. So if you wanted to ask them about this work or other work they're doing, you could do so during lunch. So let me just tell you the workflow. We first have to prepare our slides, stain them and cover slip them. They then go into a scanner like the one I'm showing here. This one happens to be a Hamamatsu, but you could use other scanners as well. This one does 365 slides at a time, and then you can set it and go home for the night. And the next day you could come in and all your slides will be scanned. So the cover slip slides are scanned, and then the images go up to the cloud, and they are analyzed. And this system assists the technologist in their interpretation. Again, it's a tool. So the software searches through the matrix of material. It looks for those objects of interest. It then groups them into category and presents them to the pathologist in a software as shown here. Now, the technologist can choose to accept that classification. So you can see here, Dientamoeba fragilis is checked off. Maybe you can't, that's a little small font. The technologist agreed that that is a parasite called Dientamoeba fragilis, checked it off, and then that transfers over into the lab information system. But remember, it's much more sensitive than, well, I should say, it's a screening tool. It's going to find multiple things. In this case, it found a few instances of other things that it called parasites that were not parasites. Our technologists can quickly screen through those and just say, no, those are not true. So here's two of my technologists looking at a double microscope or a double digital display, and then they have their microscope. And again, all positives or questionable positives are reviewed by traditional microscopy. So this works really well in a setting where your positivity rate is only 5%. Clearly, this would not work in a setting where your positivity rate is 80%. You might as well just look at the slides themselves then. So I want to now focus on what I thought would be of interest to this audience is, and as we heard from one of our earlier speakers, can you just plug and play AI? And the answer is no. You really have to optimize your workflow, and you should. You never want to apply AI or automation to a bad workflow. It's just going to make it's going to stay a bad workflow, but now with AI. So we analyzed our complete workflow end to end, and we adjusted it before we even got close to implementing the AI. So one of the first things we noticed is that the slide preparation was very important. Think of this in cytology before you had thin prep. Remember all those slides with the smears? They were very thick. Well, that's where we were in microbiology. And you can see from this top row here, this is stool that was taken right out of the container and then put on a film on a glass slide. Some of my technologists like to use this zigzag formation because it provided thick and thin areas, which they thought helped them review the slide. Well, that's all well and good if you're using light microscopy, but if you're trying to digitize this, it is, unless you want to start getting into Z-planes, this is not going to scan well. So we had to optimize our slides for digital scanning. So this is now what we went to on the bottom. We tried to make it a thin monolayer. But any of you who are lab directors are probably then saying, well, you just went from a very thick specimen to a thin specimen. How do you know you didn't lose sensitivity? Which is an excellent question. So what we did is instead of taking the stool fresh out of the vial and putting it on the slide, we took the concentrate and put that on the slide. And for those of you who know microbiology, you may know that we use a concentrated specimen for the wet prep. Basically, you're spinning it down and you're taking that pellet. So you're actually concentrating the parasites. And then if you use that on your slide, we were able to validate that we did not lose parasites. So that was one thing we had to do even before we got to digital scanning. Now, there were a few other surprises along the way. For example, our labels were overhanging on our slide, just a tiny bit, but look at that. So you put that into an automated scanner and now they're going to start sticking and they're not going to go very well. So we had to get new labels. But the problem was with the new labels is that our long barcode wouldn't fit on the new labels we got. So we had to create a new barcode and we had to validate that before we started our AI. The other thing is that we used to look at our slides one at a time. Our technologists would take the specimen, they'd put a drop of immersion oil on it, they'd put their cover slip on, look at it, and then if it was negative, they'd throw it in the bin. Well, now though, we have to create all of our slides for scanning with cover slips, and that's 200 or 300 at a time. And then we're going to scan them. No one wants to sit there and cover slip all of them. Plus, we were using immersion oil, which it's not permanent and it moves around. You can't put a cover slip that's going to move around into a scanner. So we needed a fast drying mounting media. So we introduced, like anatomic pathology, an automated cover slipper. We validated 2 different versions and then we picked one that actually articulated with our automatic stainer. But of course, we had to validate that before we could start digital scanning to make sure that it worked, that there weren't air bubbles, that it didn't change the optical qualities, that they still scanned appropriately. We didn't think that they would be, but we still had to validate that to show that that worked. So at this point, we also decided to simplify our processes. We consolidated to just a single version of the trichrome stain, which happens to be a commercially available stain called EcoStain. And we showed that that worked with all the different types of specimens we accepted. We also stopped accepting anything that had mercury or copper in it. So we accept EcoFix, a commercially available single vial fixative, and then also the traditional formalin and PVA, but nothing with mercury or copper. So now we are finally ready to validate the AI. And so I think that that was one of our major takeaways is you really should spend this time with your system before you even start your validation of the AI. Now, in the United States, this is not FDA approved. We did need to validate it as if it was a full laboratory developed test. So that means looking at accuracy, analytical sensitivity, analytical specificity, precision, reference range, etc. We did all of that and we were able to confirm that the performance characteristics matched what was seen by the group that actually created the algorithm. And again, this is locked down for clinical use and it's now versioned. And if there were a new version to come out, we would actually have to validate again, depending on what changes were made. Okay, so I'm not going to get into the validation, but if any of you are interested, I'd be happy to tell you about that. But essentially, we did look at all of the different parasites that had been trained, that the algorithm had been trained on. But now let's talk practical components. What do we do for quality assurance? What do we do for proficiency testing, quality control, training? Okay, well, so how do we handle EQA, external quality assurance? Well, unfortunately, at this point, our EQA provider, which is the College of American Pathologists, they do not provide slides that are amenable to digitization. They're too thick. So until we start getting thin monolayers from a concentrated stool specimen, we're going to have to examine those manually. Now, thankfully, that is okay because our all of our positives are still confirmed by manual microscopy. So it's fine you just have to realize that your EQA is showing that your technologist can still find the parasites, but it's not testing your whole system. So we do an alternative assessment of proficiency for the entire system. We also have our daily QC, which shows that our whole system works. We introduced 4 levels of control. So if any of you are thinking about implementing an AI system, you should think about this before you bring it in. What are you going to use for your EQA or proficiency testing? Is there anything commercially available? Are you going to have to use an alternative assessment of proficiency? What are you going to use for your quality control? Are you going to use 1 positive and 1 negative? We went with 4 to evaluate our whole system. So we have The entire process covered: staining, scanning, AI analysis, technologist evaluation. Our positive control is something we rotate periodically amongst 4 different protozoan parasites. We also have a control for white blood cells and red blood cells because our technologists just really like the way they stain, and they feel like it's a very good quality control for our staining process. And then we have a negative control. So those are made up from a stool specimen every day, and then they go through the entire process along with the patient specimens. But we also have this thing called a drift control, which is not made up fresh every day. It is a slide. It's the same slide. It's already been stained, and we use it day after day after day. And the purpose is that this pre-stained slide is scanned each day to ensure that the scanner and AI combination is detecting the expected quantity of parasites. And we had already determined that by running it 20 different times on different days. So for example, we know that there's about 100 to 200 Giardia in this particular specimen in the area that's scanned. So if we run it every day, we not only expect to detect Giardia, it better be within that range. If it only detects 5, then that's a red flag to us that something went wrong with the AI algorithm. It would have passed as a positive control if we hadn't added that quantitative component. Okay, now training, I'll just say a couple words, which is essentially plan for more than is anticipated. So just like an AI model must be taught, recognition of morphologies through that digital lens also has to be taught. We had our subject matter experts that helped validate this, and even they noticed they got better with time. And they started realizing that things that they had called indeterminate initially or equivocal, as they pulled them and reviewed them, they got better at recognizing that they were actually positive for specific parasites. Now, also the comfort with the use of technology did vary amongst our technologists, and that did affect the acceptance of the technology. Thankfully, no one left us, but it is something to consider. Okay, monitoring performance, methods for monitoring performance. We do our annual competency assessment. We do periodically review negative specimens. We have not found any negatives, any positives that were missed by the AI algorithm, but we have found a couple positives that the technologists missed, because remember, this is a tool and they can choose to accept the results or not. So that just required additional training. Any kind of AI, nothing's going to be perfect, and stool is a very heterogeneous specimen. And then we periodically introduce blinded specimens. So how do we measure success? This is another thing that I would say you should really think about before you implement is, well, first of all, these systems cost money, the scanners, the software. Think about when you're bringing this forth to try to convince your boss to allow you to buy the system, you're probably going to have to show or describe what you expect to gain from it. How are you going to measure that? So we gave this thought before we implement it. We expected our review time to decrease significantly, and it did. We were very pleased to see that. Our technologist time of these trichrome stained stool specimens went from about 4 minutes to 1.5 minutes. That was all comers, on average, a 62.5% reduction. But what I was really excited to see is that review of completely negative specimens, which is about 90% of our specimens, went from 5 minutes to 30 seconds. So that was a 90% reduction. Overall, we had a 34% increase in capacity. So this was reflected in our turnaround time. You could see these bars. Ooh, they're a little washed out, but there are some bars in the background here, and that reflects our volumes. Our volumes were going up and up and up. And unfortunately, this line here was our turnaround time, which was also going up and up and up. It was no longer sustainable. We had to do something. And that's when we pulled the trigger and we actually implemented AI a little faster than we thought we would. So where we implemented it, you can see now that drastic drop. That was our turnaround time. And as we trained and had new technologists approaching the software or the using the system, it dropped even further down. What you might not be able to see is that our volumes remained high. Our volumes were were up here, our turnaround time went right back down. We also looked at our positivity rate because we saw increased sensitivity that did reflect into detecting more parasites. We went from 3% up to 5%. And I have an asterisk up there because I want to remind everyone that all of these are confirmed as true positives. So this is not false. These aren't false positives. These are true positives that are being detected. And I'm really proud of this slide. This is our staff satisfaction. And you can see here, mental demand, the far left, did go up initially. That was over the first year. But physical demand went down, time pressure went down, difficulty of work went down. And notice this right here, performance satisfaction, pre and post went up significantly. Job satisfaction went up and ergonomic strain went down. So I see this as a win-win. This is definitely the kind of situation that you want to see. So challenges, I know I'm just about out of time, so I'll just say that you do have to overcome bias. Now that the AI is telling our technologists, hey, there's a Giardia here, they tend to believe that the AI is right. And so we have to make sure that they still use this as a tool and not as the definitive of what's there. And then I will also say that take-home points, this is indeed revolutionizing clinical microbiology, but we still need to consider the entire process. Don't apply AI or automation to a flawed process, and consider upfront what gains you are expecting and then plan on measuring them. Also, include more time to train than you would initially project, and be cautious of introducing AI bias. The AI is not always right. You need to keep the human in the loop. So I believe we have maybe 2 minutes for questions. 12:25 is what I have. Thank you very much.